Okay. Good day, everyone. Uh, and I particularly very thankful to Olga for and his team, her team, for inviting me for the talk. And it's a great opportunity to share our ideas on diamond-based hybrid qubit system for quantum computational technology. Well, I'm Somnath from South Africa, as you know. Now, South Africa is quite famous for precious metals, gold, platinum, and most importantly, diamond. Now, today, I'm going to show you how you can think of a diamond-based quantum technology, a qubit. And on this slide, you can see a piece of device made of diamond, and I will explain everything about this device. So this is a so what is the purpose of this talk is that, let's say if you want to make a very new type of qubit, then you are collecting some signal from the deep space and you want to analyze using a quantum computer. So here is the demonstration, and I'm very thankful to the funding agency, especially NRF, National Research Foundation, South Africa, and of course my own university, Wits University, celebrating 100 years anniversary. And also I'm very thankful to the companies who helped me to develop this device, analyze some data, perform experiment. And this is the logo of our lab. You can see details. It's a little bit oldish, but you can see some of our activities in the website. So just to introduce you, we are very far from America. And this is the city of Johannesburg, South Africa. And I believe my university, Wits University, is somewhere here. It is a 100 years old university. I think it's one of the largest or the largest university in African continent. We have more than 35,000 students in the university. We have many different courses. We have a large faculty member, I think more than 30 in our School of Physics. And today, the outline of lecture is it's a little bit distributed. I hope I can finish on time. So I will touch these points. One is the new quantum materials, which is superconducting material diamond, boron-doped diamond, nanocrystalline diamond. And we'll see some of the results here. And then I'll move on to qubit structure. And this is one of the type, a resonator, quantum simulation based on IBM. And if you have time, you can see the large application future. There's no end, basically. So just to give you an overview of the lab, just showing you some instrument we have, the major facilities in the lab. There are many others, but the major facilities that we have electron beam lithography system here from Joel. Some we are setting up for optical measurement NV center. We have 300 millikelvin, 10 years old instrument, high magnetic field, 12 Tesla, and the newly developed diamond deposition system. And here is the thing that we are very proud to show you, that Oxford dilution fridge. It can take you 10 millikelvin temperature. We have a vector magnet, 6 Tesla, 116, 12 RF lines, and most importantly, we have optical fiber. So you can do electro-optic measurement in this setup, and this is ready for qubit measurement. Okay, now I just want to show you for general audience what qubit means. So you have to accept the revolution, the technological revolution. And the first revolution came in microelectronics long time before. So from vacuum tube to small transistors and the chips, Intel i9, Xeon, etc. So miniaturization. And then this was very useful for space mission. Now, this is also not very new today, that the qubit was thought that it would bring fourth industrial revolution. Now we have from IBM more than 100 qubits in a chip. I have visited some of the places, IBM, NASA, etc., and I've seen these facilities. So what qubit means? If you compare with the classical bit 0 and 1, you can have qubit like a. I hope you can see the ball. Can you see? Yes. So here is the. It's my memory actually. I borrowed from someone. So this is the thing you can rotate, like you can do it here. So 0 and 1, you can rotate the vector between 0 and 1, and you can have many possibilities. The superposition of 0 and 1, and you can change this matrix, and you can do the calculation. So you can store many information by rotating this ball, and it's called block sphere. And although it looks very simple, but it is really very complicated, and it will be very complicated towards end of my talk. So you can have the rotating the ball, you can rotate the qubit. So how do you rotate the qubit? I'll come to that point, but we believe, like many people, the superconducting qubit has a good future, because it is commercially available. So what is superconductivity is that you can have a transition at at a temperature, you can receive zero resistance of a metal. And based on two superconducting junction, you can put an insulator, you can create a junction called Josephson junction, after the name of Josephson. And this is very important, this junction. What is the property of the junction? So you can really change the characteristic of property, like you can create bound state, localized state in the junction, and you can control the current, tunnel current, super current between these two superconducting leads. So you can, if you make a loop with the Josephson junction, you can have positive and negative direction, I mean clockwise and counterclockwise direction of the current at the same time. So this is called qubit. You have two-level system. It can move this way. I am just showing the hand waving way. It's not the exact way, but the thing is that it is very similar to the atomic model. So nucleus and the hydrogen atom, the electron, you can replace them by magnetic inductance and capacitance, and you can rotate the qubit with the help of a transmission line, like microwave frequency and the gigahertz frequency. And so the qubit can rotate, and basically you can have a different kind of qubit. Instead of this Josephson junction, the fire alarm is off. I think you can have a better quality of sound. So this is a different kind of a qubit, which I will explain. You can have topological qubit. You can have a nanowire of a semiconductor placed on superconductor, etc., which is not achieved today. So what is achieved today? Thanks to IBM, we routinely use this IBM quantum experience. It's extremely versatile, and it allows simulation using microwave pulses. It can do many different kind of algorithms and problem solving. But it is it can do the quantum chemistry very well. On the other hand, it is a little bit noisy. At least from our experience, we can pick up noise. So it requires error correction, etc., etc. So we are thinking how to improve the quality of qubit for IBM. And that's why we are thinking, like many others, having a spin qubit operation. So how to add spin. So here is the thing. I'll just speed up. Now, a hybrid system. So like a graphene diamond, two different things. You can put together, you can create a superlattice structure. You can have nanocrystalline diamond, your favorite material. So diamond grains separated with grain boundaries, which is made of graphitic carbon. So you are mixing, you are combining magnetism and superconductor together. You can put spin, orbit, charge, flux, etc., etc. You are using basically two different things. One is the optical microwave, one is electrical microwave system. So here is the thing. Let's think of a material where you can have both magnetism and superconductivity present. They coexist. And this is the main part of my talk today. So here is the things we are going to show: spin, orbit coupling, how it works in superconducting diamond. We can extend this work for phase slip junction, etc. Okay, so once again, this is the last slide for introduction. I'm taking long time basically. Okay, so it's not we are the first people who are thinking NV center and diamond, putting superconducting qubit together. So people have worked on superconducting qubit and diamond. They put them together. They're using the quantum processor of superconductor and the quantum memory of NV center. As you know, NV center is great for quantum memory because it has a very long coherence time. But it has not been so successful because the coupling between these two different units, aluminium to NV center of diamond, it's not so easy. People have just done it just very casual way, although it published very important paper. So how do you understand the whole things? Basically, you need a better quality of superconducting qubit and NV center. So we wanted to add in these things better functionality like quantum phase slip junction, holonomic gates, three-qubits, etc. So the first part of my talk, as I said, that we want to see the power of diamond, boron-doped nanodiamond fields. So these all papers are published thanks to the people who published the papers. And what is new in this material is that before going to superconducting state, you can have basically a peak of resistance peak. And that was explained by us as a Kondo effect, or charge Kondo effect. And this is the signature of you have some spin impurity in this material. It's not from the impurity of any standard material, but it is the property of the material, basically, how it creates the localized spins. Not going to tell you the details of the analysis, but if you feed the data using the Halperin-Nelson formula, and you can see some kind of transition which is called Berezinski-Kosterlitz-Thouless transition, and this kind of mechanism got Nobel Prize in 2016. It's quite new, although the subject was very old. So we understood that although diamond is a 3D material, as you know, in nanodiamond you have the layers or planes which is two-dimensional. And this is a very interesting hypothesis, but we have done the high resolution, I would say ultra high resolution transmission electron microscopy, which is done in a diamond light source, Oxford, in collaboration with Oxford University, thanks to the people. And So what you see, the grain boundaries, I think this is the best quality picture of nanodiamond we have ever seen. And you can see the twins, this kind of angle 45 degree. And this is the microstructure which can be compared with the electrical transport. Namely, when you rotate the sample as a function of magnetic field, you apply the magnetic field, and you can see a periodicity which is nearly 45 degree. So it matches with the microstructure of the sample. So we can say this microstructure is very important for the transport property of the material. Now, if you look at again the grain boundary, grain 1, grain 2, these are superconducting grains separated by a grain boundary region, and you have the charge accumulation in this grain boundary region. And there's a model called Edelstein effect, which is similar to Rasbach spin orbit interaction. So what you do is a spelling mistake, sharp translational symmetry breaking. It takes place here because the potential is broken at the boundary, and you can see the effect like Rasbach type spin orbit coupling. Now, once you have, what is the proof? If you perform the magnetoresistance of the material, you can see a positive magnetoresistance. And this is, it's well known, weak anti-localization. And this is the signature of spin orbit coupling in the material. Now, what does it mean? Is that you can have the spin singlet just like a BCS superconductor S0. Now you can have, in addition to that, you can S is equal to 1. The total spin is equal to 1. So you can have spin up, spin down, and a combination, linear combination. And this is the very expensive to see in the materials. In superconductors, we have been very fortunate to see this effect. So what is the proof? Once again, if you perform the differential conductance, so you do IV measurement, current versus voltage, and you convert this into the differential conductance, and you perform this measurement at different temperature, 300 millikelvin onward. You can see at zero bias, zero field, you can see a strong peak with some satellites, which is temperature dependent. I'm not going into details because that's not the main topic of my talk. But what I want to say, this is a very, very important signature of non-BCS type superconductor, unconventional superconductor. It's very difficult to see in normal superconductors. So if you perform this experiment as a function of magnetic field, you can also record these things. It's sensitive to magnetic field. Although we published the paper, there are many, many things to be understood in the material. To be frank with you, we are doing more calculation, simulation of the data. Anyway, so there's one more interesting thing which is not observed in BCS type superconductor, because you have the junction, grain boundaries. Remember that I said the junctions or boundaries are very, very important in the superconductor. So you can create a junction which is called pi junction. So you can have a change, pi phase change of this superconducting phase. And you can see this oscillation, periodic oscillation at different temperatures. We have many more data, but I'm just showing you some of them. And you can do Fourier transformation, and you can calculate the size of the grains from these oscillations. So from this expensive data set, we can make a model of the material based on the microstructure, that you have grains and you have zero junction and pi junction. And this is very important. This is the signature of the nanodiamond, and this will be very important for making a new kind of device. Just before I conclude this chapter, this part, I just wanted to show you one more very interesting things. Now, here you see, you can model as a nanowire, a thin wire of diamond, basically through the grain boundaries, right? Now, what is the signature of the signal? So this is a pretty new subject. It's called quantum phase sleep junction. So you have a duality between flux and the charge in this material. So how does it happen? So if you take two superconductors and there is a junction, you can have this Josephson tunneling, but you can change the structure a little bit. Just superconductor connected by a thin wire of superconductor, a nanowire. Okay, and then you can have this phase sleep kind of junction, and you can see something. It's called quantum phase sleep junction. You can see 0-point fluctuation and many other interesting things, oscillations, etc. Now, this actually inspired us to make a new kind of device, because the Josephson junction, making a Josephson junction for diamond is not that easy. So this is just the alternative approach of making a phase sleep junction. So now we get back to the original picture. This is the junction, and this is the model. And if you feed the data using the quantum phase sleep junction, and you can see there's very good fit, that means it can work for this material. Okay, so here is the things. Now, instead of Josephson junction, Flux-qubit, we have designed using the diamond. I'll show you in the next slide. So we just created a diamond junction by ion milling. I'll show you in the next slide. And it can show also this kind of spin-triplet features, and it can also create a very strong coupling. More experiment to be done, by the way, but you can also combine the nitrogen-vacancy center in the same platform. Let's see. Now, I think I will spend more time on the images, which people will like, I believe. So very thankful to Zeiss. I have to travel to Boston, basically Peabody, to look at the experiment. So there are great technicians who did the experiment for us. So this is a Orion nanofab. Basically, this is a helium ion microscope. And so this structure is created by helium ion microscope. And this is a resonator, diamond resonator. And you can see this is the meander and one part. And if you zoom in, you can see this kind of resonator. And you have seen this kind of junction nanowire, and that is arguably the quantum phase sleep junction. Well, and this time it is 30 nanometer, but we can have even thinner. But let's see the results. So if you run, you just do the microwave transmission through this resonator, and if you compare with this kind of R versus T with this S/1 transmission coefficient, and as a function of applied bias, 0 to whatever, and at different frequencies. And you can see this absorption or transmission through this color graph. And this has a very strong overlapping between these two slides. And you can see that as if there is a resonance which is taking place, a standing wave, because of the structure of the material. Now I can show you the next structure which is more appealing. If you see the phase of the wave function or wave, and you can see very strong resonance at a frequency of maybe 5 to 6 gigahertz, and which finds very similarity with this current versus temperature dependence. This is the first experiment we have done, or somebody has done, for diamond resonator. We are about to publish this work, but it requires more calculation analysis. It's very complicated, you understand. Now I'm just quickly showing another measurement which is not very accurate, maybe more measurement to be done. But if you vary the structure, you can see difference in the measurement. Anyway, so this structure, this quantum phase slip junction, and that can be really coupled, few of them, and you can have an array of them. So you can create a different kind of, which is called top flux or phase slip qubit, top transmon, different kind of things. If you ask me at the end of my talk, I can answer to this question. But the interesting things, since we have seen the bound state or spin-triplet kind of things, this has a great potential for topological qubit, which is our ambition. And even the people worked, our students and postdocs, they wanted to do that, but it's really not that easy. Today, I'm showing you something very simple, which is very convincing, not the Majorana fermions topological, but I'm not showing it today. So here is the nanowire. This is diamond nanowire, and this thickness is that 18 nanometer, 18, less than 20 nanometer. It may be possible even slightly smaller, but it can break. So what I wanted to show this time, next half an hour, I have 20 minutes maybe. Okay, I want to show you basically what is the power, what is new in diamond vacancy center. I am sure the audience know much better than me about the NV center. They have done extensively. We are specialists in electrical transport. We are starting basically the proper measurement of NV center, but in a different direction. But what we have done last few years, we have published a number of papers using the IBM quantum simulator, quantum experience. And these are all on NV centers. So we have simulated. Oh, by the way, I just wanted to tell you I forgot to tell you. So we have been working on nitrogen-doped or nitrogen incorporated nanocrystalline diamond for many years, last 20 years. Even we have started recently working on nanocrystalline diamond in nitrogen doped, and our students published several papers over the time, and even the theory models, etc. So what we wanted to do, the simulating the NV centers basically. So the NV center has electron spin, nuclear spin, etc. And you know better than me. Now you can replace them by the qubit, superconducting qubits. Now we think we are the first people who have shown, especially our young student, that using a superconducting qubit you can simulate NV center, nitrogen vacancy center. This is a very good achievement. Not that difficult for one qubit. And it really reproduces the work people have done experimentally. We have simulated the work basically. Now, there's people are very skeptic about the usage of NV center. How do you make NV center? How do you really apply this technology? We don't know. But we know that we think we know some trick how to do that. Let's say you have 3-qubit system. So here is 3 NV centers. So again, a very young student have performed the simulation, and with 3-qubit system, not only symmetrically positioned, but in a very asymmetric manner. So what is the performance of the 3 NV centers? Asymmetrically coupled. And this is the circuit, quantum circuit. Maybe it will take time to explain all these things, but I just want to show you very important results. So here is the things equilateral and with some of the disorder basically in this triangle, but you have final the scalene completely disordered, random configuration. Now, if you tweak the coupling between the NV center with the microwaves, microwave pulses, you can gain a very high coherence time, operating time, something like 10 microsecond or more. This is a big achievement. So you can really configure the qubits, nitrogen-vacancy center. You don't have to worry about the position, etc., but still you can. Now, what is new? What is new? What is new? And this part will be very difficult. I don't know how much I can explain to you today. This is a very, very interesting subject. Now, NV centers is not just, it's very special. It has magnetic properties. It has ground state, 0 plus minus 1, but you have excited state. Very, very few people use the excited state of NV centers for computation or experiment. People like David Ashalom from the University of Chicago or Lloyd Hollenberg from Melbourne, and few people, they took the opportunity to show the theoretically how this will work. And this is called holonomic gates. I'll come to that point. So you can use a 3-level system, and you can use the dark state of these NV centers. Now, as a combination of this ground and excited states, you can create the dark state. Also, you have the bright state. So these kind of things will create a new kind of qubit. So you see this rotation, we create a space or area, and the solid angle is very, very important for this computation. But this is very similar what we claimed in superconducting diamond, the bound state. But the advantage of this dark state is that it can remove dynamic phase shift, and it can improve basically the fidelity of the system. Well, it's a very new approach. It's not been experimented by many groups, but the calculation shows is a great future. So this geometric phase is the most important thing for the quantum calculation. People tried using NV center placing on superconducting qubit, not diamond. And there are signature of these dark states, but it didn't work that well. So we wanted to do something, we wanted to combine quantum phase sleep and this kind of situation. So once again, you can see once you run this qubit, if you rotate, you can create non-abelian phase, and that you can accumulate from the qubit rotation. If you have question, please ask me at the end of my talk. It's complicated. But what is very important, I want to show you some of the results. So it is done with the IBM quantum simulation. And then this shows for single qubit and the double 2 qubits. I'm sorry, 2 NV center, basically, which is concatenated and combined. And the most important thing, if you use all these NV center, all these levels, ground and excited states, you can have basically all these things, they are coupled, and you can create 3 dark states. And if you get 3 dark states, you can basically do all these geometric phase calculations. Basically, so this red line shows without holonomic gates, and now if you add this holonomic operation, you can get the different phases. Well, I forgot this. This paper is available on archive. Forgot to put the reference. You can check by my name. Okay, so we are very successful in creating non-abelian geometric phase using 3-qubit system of NV centers. Now the application is that if you have 3 qubits, you can create a color qubit. You can have optimization, image processing, lots of things you can do, which is a future technology. You can combine the holonomic gate of superconducting diamond and with the NV centers, which is nobody has done this, by the way. You can have a very complicated quantum network in this system. It's very difficult to show all these results just by rotating the ball. It works in Hilbert space. It's very difficult to say otherwise, but it has a great future basically to handle this 3-qubit system. Now the last 2 slides. So we have, as I said, we have acquired a new dilution fridge, and this has a 12 microwave lines, and most importantly, it is coupled with the optical fibers, multi-mode optical fibers. So you can do the electro-optic operation of this nitrogen-vacancy center and the superconducting qubit. So you need such an instrument to do the experiment. We have some facilities, not everything. I must tell you, we are still trying to buy more components, electronics. If we get more funding, it will be nicer. But we can do some unique experiment using the setup that combining electrical and optical things. So this is the things our students are trying to establish a setup for electro-optic measurement using 2 different kind of lasers. So I try to explain basically today various things: microstructure to oscillation, zero bias peak, quantum simulation, and this kind of resonator structure. And now the most important part: who did the work? Well, it is shared by many people. So some of the students, they have started many years before, and but they are no more in the lab. But I'm very thankful to the students present and past and the future. So the question is that the acknowledgement list could be very, very long, but just to summarize, because I think I spent already 40 minutes. So very thankful to Zeiss, Professor Nesladek, Professor Silva, Professor Flohot, Olga Tarabdar, Victor Setlan, and many more, and the people who worked in this field, Chris Coleman, Venkat, Devi, Ilya, another Chris from, and many others. Basically, Dimitri, Ross, many people who contributed for the project. And I think I'll stop, and thanks for listening to the talk.
Somnath, thank you very much. It was very illuminating talk, very complicated topics, but definitely very exciting. So we are open for questions from the audience. please feel free to type your question in chat area or just unmute yourself and start asking in live your question. So far, I will start with my question. Being a material scientist, so I would like to learn more about this exciting boron-doped nanodiamond material, more details, probably level of doping, of boron doping, how much boron do you have in the films, and what is the minimum requirement for this, as well as existence of other possible maybe boron carbide presence there, or so how you make your nice films.
Yeah, I just want to tell you this boron doping is done in the group of Professor Milos Nesladek in Belgium, Hasselt University, and he was very kind to offer me these samples, donated basically, and it was done by microwave CVD basically. And it's grown on quartz substrate, and the doping level is varied. Actually, boron percentage was varied from basically over a few percentage, but the level of doping was 10 to the 21, something like that. It's all written in the our publications. I have not shown some of the slides. I have to go back. So the details are written in the things. But what is important is that in the processing, you can change the size of the grain of diamond or nanodiamond, and which varies from 40 nanometer to 100 nanometer. So that is the range basically. So it was done that very carefully. And these samples showed the superconducting transition, which is from I believe from 0.8 Kelvin to nearly 3 Kelvin, 3 to 4 Kelvin. I don't remember exactly. I have deleted them. I didn't want to show the slides because it will take time, but we have done all 4 to 5 samples we have measured. Actually, we have measured many samples, but 4 different kinds of grain size. And this is the thing which we have shown the best quality, which shows something 2.7 Kelvin at the superconducting transition temperature, which is very, very good. But you can also improve the doping level. Some people claimed the superconducting transition temperature, they could achieve 10 Kelvin, which is, and some people even claimed 25 Kelvin earlier days. But I have not received those samples, but we don't need them also. Then we wanted to see this kind of the beautiful properties of this transition at low temperature, and we have the facilities like dilution fridge, etc. So we don't need really high temperature samples. But these results are very consistent for different variation of grain size. I hope I answered your question, but if you have more questions,
it's very clear, very good answer. So
yes. And the coherence length also a few nanometer, which really compares with the aluminium superconductor. So that is a very good thing. The properties of material is quite similar to aluminium, which is a very, 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 very standard superconductor. But we see some additional features which is not seen in metals. Yes, that is the thing.
Okay. So if somebody has question, just please unmute yourself and start talking. So maybe I will ask more about nitrogen vacancy center. So you mentioned that it's hard to control its creation. And one of concerns is that since grain size, or maybe this grain size is quite large, if it's between 40 nanometers and 100 nanometers, in principle, spin properties of NV centers created in such relatively large grains probably should be reasonable.
This is a very good question. You see this new instrument, diamond instrument. And yes, one of our students is working on the doping of this nano diamond. This is also micro FCVD we have. Yes, that is the target. But we have bought the sample from De Beers element 6, which has very few nitrogen vacancy center. They say 1, 2, 3 NV center in the entire sample. So we wanted to have, ideally we want to have one platform. You have a superconducting diamond and combined with NV centers. It's not, I'm saying that as if it is very simple, but it's not that simple. But it is doable. It will take years, several years to establish the material properties, both nitrogen and boron present in one carbon system. It's you know that it's a very classic problem. How do you?
Did you consider to use then nitrogen implantation as it is done in many single crystal diamond works?
Yes, we do not have the facility in our lab, but we can collaborate with other groups basically if they like. Yes, possible. It's well known. In fact, in South Africa, we have people, one of my colleagues basically in my department, he is an expert in the ion implantation of diamond. So we have Ithemba lab, national facilities, very good facility. We have this, it's possible. But everything costs time, basically. I mean, so many things, yes, we can do that. But still, controlling nitrogen vacancy center in diamond is not that easy. I must accept this.
We have a question from Daniel Wambangi. Is there singlet state superconductivity in nanocrystalline diamonds? And how do they compete with the triplet state in your sample?
So Daniel Wambangi is my good colleague. We are in the same building actually. I saw him half an hour before. He can he ask the question basically, or you don't allow people to ask questions, do you?
Oh, please, Daniel, please unmute yourself and ask your. He doesn't have voice audio connection. So,
no problem. No problem.
You
so the
can
question
read
is
his
that
question in the chat room.
Okay, I think I have to see the chat room.
It's at the bottom.
Oh, okay, okay. So hi, Daniel, you can hear my voice, right? Okay. So this is a very, very intelligent question, basically. Yes, you have, if you have a single crystal diamond, the most important thing is that you have a conventional superconductivity, like S-wave superconductor. Now, if you reduce the size of the diamond, and if you have grain boundaries, so the most of the thing is controlled by the junction, tunnel junction between two diamonds. So that is, as I said, the effect is like a spin orbit coupling. And the paper we published, it was accepted based on that claim. It was a kind of Edelstein effect. And so you create a polarization basically in the in the grain boundaries, and that creates basically this kind of, they breaks the symmetry, translational symmetry breaking. So that creates a non-S type superconductor. But you can have a mixture of S wave and non-S wave in the material. You can, I mean, it's not a bad claim. People have made this.
Mm-hmm. So it seems we have no more questions. So unless somebody wants to learn last minute something else in addition to what we heard. So I would like again to thank Somnath for his very interesting talk. This topic is so much different from what we heard previously, and kind of refreshing all these exciting opportunities from superconducting diamond films, and now combining them with all these spin capabilities of NV centers sounds as very, very interesting and far-reaching topic. So I wish you good luck with in this exciting research area, and hope to read more exciting publications in the near future on this topic. So on behalf of everybody, I would like to thank you, Somnath, again for presenting.
Thank you. Okay. Can I